this video, we're going to be covering some more of the advanced parts of integration for year one of the Edexcel course. Now, before coming into this video, the assumed knowledge is that you can integrate and you understand for a basic area what integration achieves. So for that bit, I'll just summarize as follows. So hopefully we realize that if I draw the graph of y equals f of x, this represents any graph. I've just drawn an arbitrary curve to represent y equals f of x. Now, if I choose an arbitrary point A on the x-axis here, and an arbitrary point B on the x-axis there, and we draw lines, vertical lines, until we hit the graph, the area that's trapped in between the x-axis and the graph, bounded by the vertical lines x equals A and x equals B on the right, this blue area here, is found by integrating between x values of A and B, fx, with respect to x. So if you integrate y, in other words, if you integrate the function of x where y is equal to, for this particular curve, between A and B, that will give you that area. So, to start with, I'd like you to have a go at an introductory problem, just to make sure that you're comfortable with that principle. Now, I'd like you to have a go at this problem here. I'd like you to find the finite area bounded by the x-axis and the curve y equals minus x squared plus 3x. Before you have a go, I just want to clarify really what this question is requiring you to do. Unlike this example where the exam question would have to tell you exactly where A and B are, because they could be to the left and to the right respectively, and they would obviously represent different areas. However, for this example here, when you've got the graph of minus x squared plus 3x, there is a finite area trapped between that graph and the x-axis. So for this example here, I recommend drawing this graph, and you will see the area that is trapped that I wish you to find. So if you could pause the video right there, have a go at this problem, then we'll come together and let's see if you grasp the basic principle of integration before we move on to more of the advanced topics that I wish to cover in this video. Okay, so hopefully you had a go at that. Let's see how you got on. We were dealing with the graph of minus x squared plus 3x. Now, sometimes in an exam question, they draw the graph that you are looking to find, and they show you the area, which is quite nice to see on a visual level where the area is that we wish to find. But sometimes, if you've got a reasonably simple graph like minus x squared plus 3x, the examiner would expect that you know how to draw such a graph. It's a quadratic graph. Even at GCSE level, you'd be expected to draw a graph like this. So, minus x squared plus 3x, hopefully we can recognise it's a quadratic graph. And all we really are interested to do is to sketch the shape, and we can see it's got a negative coefficient, so it's going to look like this. And we're interested in the roots. Really, that's all we really need for this sketch. So if we factorise this, I can see I can take out minus x, and then this bracket must be x minus 3. So from this factorised form of the quadratic, if minus x equals 0, of course we set y is equal to 0 to find where a graph touches the x-axis. If minus x equals 0, that means x equals 0, so x equals 0 is a root. If x minus 3 is 0, then x equals 3 is a root. So, we draw our roots of 0 and 3. We recognise it has that shape, So our parabola looks like this. It extends to the left and to the right. And now going back to the comment I made before, when we talk about the finite area, clearly the finite area between the x-axis and the graph is this area here. So this example here is perhaps a little bit more complicated than perhaps what you're used to, because it didn't tell you the limits of integration. So sometimes you have to draw a graph to work out where the limits are of integration. So this is the graph that we're interested in. So, if we now perform the integration, we're integrating between 0 and 3 as we found, of minus x squared plus 3x dx, which integrates to, let's increase the power and divide by that new power, that's x cubed over 3 like so. So you've increased the power divided by the new power. Same here, this has a power of 1, so it becomes x squared, and then you divide by that new power and you get this. Now, as we know, for numeric integration, a definite integral, we now substitute in the top limit, substitute in the bottom limit, and subtract. It is quite nice, however, to notice when you put 0 in, you get 0 and 0 there, so you get 0, which is quite nice. So really, we just need to insert 3 and effectively subtract 0. So if we insert 3, we get minus 3 cubed over 3 plus 3 over 2 multiplied by 3 squared. Subtract 0. Minus 3 cubed over 3 is minus 9 plus, and this is 27 over 2, which turns out to be 9 over 2. So that is the correct answer for that area over there. What I would like to do is I would like to show you a strange phenomenon that occurs with integration. What is that? Well, let's have a look. If you take this area and you flip it around the x-axis, in theory, the area should remain the same. I'm taking the exact same area, I'm not enlarging it, I'm not stretching it, I'm not doing anything with it, I'm just reflecting in the x-axis, so the actual area has been preserved. So this graph here would turn into this graph here. Right? If you reflect it, we're now looking at that area over there. Now we know from our work on transformations that the transformation minus f of x performs a reflection in the x-axis, which means that my graph over here, which was f of x equals minus x squared plus 3x, if I'm performing a transformation minus f of x on this, then this graph here is going to become x squared minus 3x. So that's this graph here. Y is x squared minus 3x. As before, this root here is 0, this root here is 3, and the area is over here. The exact same area as before, just flipped in the x-axis. So let's perform a similar integration, and let's see what happens. So now we're integrating from 0 to 3, but we're integrating x squared minus 3x this time, with respect to x. If you perform that integration, you get similar terms from last time, x cubed over 3 minus 3 over 2x squared between 3 and 0. Let's insert 3 like last time, and insert 0 and subtract, and you'll get 3 cubed over 3 minus 3 over 2 multiplied by 3 squared, subtract 0, because you get 0 in both terms, and you get 9 minus 27 over 2. However, if you work out 9 minus 27 over 2, you get a result of minus 9 over 2. Now, this is somewhat problematic. How can an area be minus? It almost appears like we've made a mistake. If you recall, earlier on in the video, you can rewind, we found that the flipped area before had an area of 9 over 2. When you flip it around the x-axis, why should the area turn into a negative? Furthermore, how can we have a negative area? It really seems as if we've made a mistake, but I can assure you that this calculation is indeed correct. So let me explain what's going on here. This is not a problem. I also want to emphasise there is no such thing as a negative area. We have not created a principle known as a negative area. There's no such thing. If you integrate between two values on the x-axis and the graph you're trapping is below the x-axis, you will get a negative result. In fact, had we not got a negative result, we would have had a problem. What the negative result means is as follows. It means that the area that you are concerned with is below the x-axis. If the area is below the x-axis, the integration will tell you as much. It will tell you by giving you this minus. So that minus doesn't mean that the area is negative. It means that you've got an area of 9 over 2 below the x-axis. So the answer to the integral is negative. You're allowed to have a negative answer to an integral. That's not a problem. However, areas we know are positive. So really, this is an area of 9 over 2, but it's below the x-axis. So I get rid of the negative for my answer because I don't need the minus, and there's no such thing as a negative area. That minus is just telling me it's below the x-axis. So that area is 9 over 2, which agrees with the previous example, and we can reconcile the two. In my next video, I'm going to show you why this principle of having areas below the x-axis and giving you a negative result can be problematic and can cause some problems. So therefore, we have to be very careful when we're tackling harder examples of integration.